Greeting to all my friends and our lecturer, Dr. Sharifa Suhaila Sheikh Jamaluddin. We are from SSCE Section 2, and I'm the leader of this group, Lo Chiu Dong. So my group members including Erin Chen Ewan as photographer and recorder, and also Pa Wei Jin as a collaborator. So now I'm going to present my part as part 1. So for this question, the question requires us to obtain a joint probability density function of two random variables, which is x and also y. So I actually get my joint PDF from the website as I shown here, and I take the question from the example 5.15, and I wrote in this slide. Then so as you can see, fxy is equal to x plus 3 over 2 y squared for the range when x is in between 1 and 0, and also y in between 1 and 0. So fxy is 0 for the other value, the other range. So for b, the question asks us to show that the joint PDF satisfies the properties of being a PDF. So for your information, the properties of being a PDF, we have to show that the fxy is always in between 0 and 1. And also when we integrate fxy respect to x and also y, we will get 1. So in here, obviously, we know that when we sub any value x and y in between 0 and 1, we should get fxy large or equal than 0. And also when we integrate fxy respect to x and y, or maybe we can also integrate fxy respect to y and x, then we can get 1. So here we integrate x respect to x first, then we get x squared over 2 plus 3 over 2 xy squared. So we sub in the value 0, 1. So use the value of 1, then minus value when x equal to 0. Then we get 1 over 2 plus 3 over 2 y squared. And we integrate again respect to y. So finally, we can get the answer 1. So as a conclusion, since fxy always larger than 0 for x and y in between 1 and 0, and for the double integration for fxy respect to x and y, we get 1. So the joint probability density function satisfies the properties of being a PDF. Then C, the question asks us to find the marginal PDF for x and y, and also show that both marginal density functions satisfy the properties of being a PDF. So here we got the marginal PDF for x, and we denote as gx. So we have to integrate the fxy respect to y. Then we get the answer x plus 1 over 2, and the range of the x is in between 1 and 0. Then we also get the marginal function of y, and we integrate the fxy respect to x. Then we get the answer 1 over 2 plus 3 over 2 y squared, and the y is in between 0 and 1. So in order to show that both marginal functions satisfy the properties of being a PDF, we have to show that when we integrate the marginal function of x respect to x, we get 1. And also we integrate marginal function of y respect to y and get 1 also. So here we already show that we already showed that the answer equal to 1. So when we integrate the gx respect to x, we can get 1 over 2 plus 1 over 2, which is equal to 1. And also same goes to when we integrate marginal function of y, respect to y. So as a conclusion, we state that since gx and hy larger than 0 for all x and y in between 0 and 1 respectively, and also when we integrate gx and gx and hy respect to x and y respectively equal to 1, so both marginal density functions satisfy the properties of being a PDF. Next, for part 1D, the question asks us to determine the covariance and also correlation of x and y. So as you can see, the formula we have already inserted in our slide and also report. So in order to get the covariance and also correlation of x and y, we have to find the expected value of x and also expected value of y, and also expected value of xy, and variance x, variance y. So to get variance x and variance y is not enough for us to only get expected value of x and expected value of y. We have to find expected value of x squared and also expected value of xy also. So here I separate it to 3 columns. And first we get expected value of x, which is we have to integrate x gx. Gx is the marginal function of x that we have already found in the previous. So we have to integrate the terms respect to x. So from here, we got that expected value of x is equal to 7/12. And also ex squared, which is expected value of x squared. We have to integrate x squared gx respect to x. And we get the answer of 5/12. So to get the variance of x, we use the expected value of x squared minus the square of the expected value of x. So from here, you can see we got the answer, which is 11/144 for variance x. Same goes to y, but then the thing we have to change is for all x, we have to change to y, which is if we want to get the expected value of y, we have to use the integration of y hy respect to y. So we get the answer 5/8 as expected value of y. Same goes to expected value of y squared. So we integrate the y squared hy respect to y, and we got the answer 7/15 for expected value of y squared. Then variance y is quite similar to variance x. We use the same method. Then we get the answer 73/960. So for exy, expected value of xy, we have to use double integration by xy, fxy. We integrate respect to y and x. So in this case, we can actually use dx, dy, or dy dx. It doesn't matter. So we got the answer 17/48 for our expected value of xy. Then we can find our covariance. So covariance, we just sub in the value, and we got that covariance in negative sign. It's okay because covariance can be negative or positive value. So we got our answer -1/96 for our covariance x and y. So same goes to correlation for our x and y. We just sub in by using the value of covariance xy, and also we use the square root of our product of variance x and variance y. So we get answer -0.1367. as our correlation of X and Y. So my part until here, so I'm going to pass my mic to our second presenter.
Next slide. With that, I'm adjusting our image to not block the slide here. Okay, my name is Park, and now I'm presenting part 2. So part 2, the question requires us to create a scenario that can be translated into a joint probability function problem and complete the question. So now we try to think about a lucky draw competition. Then we pick out with 2 lucky people, A and B. We select them to win the final prize of the competition. So each of A and B are given 2 boxes with in box 1 they got 2 balls with number 0 and 1, and in box 2 they got 10 balls with number 0 until 9. So they are required to select 1 ball from box 1 and also box 2 respectively and form a two number digits, which is shown like in the diagram. So for example, if from the first box if I pick 1 and in the second box I pick up 2, so the digit form is 12. So the people that got the higher digits form will win the final prize. But if both A and B got the same digit, then the game should restart. So in this situation, we can use joint probability function to calculate that the probability of A to win or of B to win by different digits number, by different probability. And also the probability to restart the game. So we can see about we define that the random variable X represents the digits formed from box 1 and box 2 by audience A. So that is from 0, 0 until 19, which is +1 from the before part, before one. And the random variable Y represents the comparison of digits by audience A and audience B. So we define that when Y equals to 0, both of them get the same number. But if Y equals to 1, then A get the bigger number than B. And if Y equals to 2, vice versa. So then we can tabulate the data, the probability function into table, which is shown in the right part. So the probability can be calculated lah. For example, for the first one, X equals to 0, 0 and Y equals to 0. So from the first box, we pick out 1 ball from 2 balls. So the probability is 1/2. And the second box, we pick out 1 ball from 10 balls. So the probability is 1/10. So the probability is 1/2 times 1/10 is 1/20. And for the condition Y equals to 0, the probability to for A and B get the same number is only 0, 0. Means that that is 1/20 times 1/20 will get 1/400, which is 0.0025. So the same method used to calculate the other probability and tabulate into this table. So, and one we can notice that for every random variable X, which is from 0, 0 until 19, we can notice that the probability are same, which is because the game is fair. The ball is fair. We pick out the ball is fair, which means that the probability to get each ball is same, 0.05. Okay, and also the sum of the probability must be 1 for also for us to check answer. Okay, next slide. Uh, Okay, so now the question requires us to give an example of probability of x given that y equals to any a value y, and obtain the corresponding expected value of x given that y, and also variance of x given that y. So by definition of conditional joint probability, we can know that the probability of x given that y is the probability of xy divided by marginal probability of y. So for example, we take a value y is equal to 2. Then we can calculate the marginal probability y equals to 2, which is also shown in the table 0.475. And now we take any x value. We take any x value, like I take x equals to 15, then I can get that if x equals to 15, then the conditional probability is equals to 0.02105 for 4 significant figure. And also the similar method used to calculate the expected value of x given that y, and also the variance x given that y. So now I choose y is equal to 1. So the expected value by definition is summation x means that the all x from 0, 0 until 19, x times the function that given that 1. So for same method, function x given that y equals to 1 is equals to fxy divided by probability y equals to 1. Here is typo, is 0.475, sorry. And the then we calculate it by manually lah, or I use Excel to compute it. It's easier. So I get the final answer. The expected value is 6.175, and the variance is one more step lah. We calculate the expected value of x squared given that y equals to 1 first, and then lastly we get the variance of x given that y equals to 1 is 52.12 for all 4 significant figures. That's all.
My name is Erin Chen Ewan, and next I will present about part 3 question. The question given is obtain a moment generating function for a random variable which follow one popular distribution and state the reference used to get this distribution. The solution is let x be a continuous exponential random variable with range from 0 to infinity and with probability density function of fx equals to lambda times with exponential power of e and power of negative lambda x. If x is in 0 to infinity and 0 elsewhere, where lambda is positively real number, then the expectation of e to the power of tx is symbolized by mxt. And to get the moment generating function, we need to integrate e to the power of tx times with fx, which is equals to lambda times with e to the power of negative lambda x from 0 to infinity. Since lambda is a constant, we bring out lambda and factorize x in the power of e, and we get e to the power of t minus lambda x, and which is finite only if t is less than lambda. And we get the moment generating function is equal to lambda over lambda minus t. For question B, find the expected value and variance for this random variable using moment generating function. Expected value of x is equals to m prime t, which t is equals to 0. And we differentiate mt, we get lambda divided by lambda over t squared. And expected value of x is equals to 1 over lambda. In order to find the variance x, we need to find the expected value of x squared. And expected value of x squared is equals to second derivative of mt. By differentiate m prime t, we get 2 lambda over lambda minus t to the power of 3. By substituting t is equal to 0, we get 2 over lambda squared. Variance x is equals to expected value of x squared minus expected value of x squared, which is equals to 2 over lambda squared minus 1 over lambda squared. The variance is equals to 1 over lambda squared. That's all from us. Thank you.